The derivative. It's the instantaneous rate of change, or from now on I may just say rate of change. When you don't qualify rate of change, it means the instantaneous rate of change as opposed to the average. The derivative is the instantaneous rate of change, and if the mathematics is modeling our intuition correctly, there are some things that should be true that we don't know are true yet. So, for instance, we don't really know that if the derivative of a function is positive, then the function is increasing. Intuitively, that sounds true. If the rate of change of a function is positive, then the quantity is increasing. For instance, if the rate of change of the money that I have is positive, that's a good thing. It means that as time goes on, the amount of money I have gets bigger. That would be good, but we don't actually know yet that just because the derivative is positive, the function gets bigger as the variable gets bigger. There are other intuitive things that we don't know yet. Suppose you throw a ball up in the air. As the height of the ball increases, the derivative is positive. That we actually know already. If the height is increasing, the derivative is positive. And then as the ball starts to come back down, the height would be decreasing, so the derivative is negative. So the derivative is positive as the ball is going up, the derivative is negative as the ball is coming down. What happens right at the top when the ball is at its highest point? Well, the derivative should be 0. But we don't really know that yet. We don't really know that when a function attains a maximum value, so the height attains a maximum value, that the derivative has to be 0 there. We'd like to know that, but we don't know it. Another example of intuitive things that we don't know yet, suppose you're in a car and you travel exactly 60 miles in exactly 1 hour. Was there ever a point in time when you had to be going exactly 60 miles an hour? If you think about it for a few minutes, you'll probably conclude that the answer is yes. And the reasoning goes like this. It's, well, if I went 60 miles an hour the whole time, then of course there was a time when I went 60 miles an hour. So suppose I didn't go 60 miles an hour the whole time. Well, if I went under 60 miles an hour the whole time, then I would have averaged under 60 miles an hour. But I averaged 60 miles an hour. So I couldn't have gone under 60 the whole time. Suppose I went over 60 miles an hour the whole time. Then I would have averaged over 60 miles an hour. But I went 60 miles in 1 hour. My average velocity was 60 miles an hour. So at some point I had to go under 60, and at some point I had to go over 60, and in between I had to pass through 60. So yes, we believe that if you average 60 miles an hour on a trip, there was a point in time when you had to go exactly 60. In mathematical terms, that means at some point the derivative should equal the average value of a function on an interval. And finally, most intuitively, something you may think we know already, but we don't know that if the derivative of a function is 0, then the function has to be constant. Intuitively, that better be true, or derivative's not working correctly, because what we said is if the rate of change of a function is 0, the function is constant. Yeah, that should be true. What we know is that the derivative of a constant is 0. We don't really know that if the derivative is 0, then the function had to be constant. In this section, we want to look at all these things and show that they are true with the right technical hypotheses so that the derivative is working the way we want it to in these cases. So let me start with an example. I want to start with a function y equals x squared, so its graph is a parabola, but I want to artificially chop off the domain. I want to say that x has to be greater than or equal to -1. I'm doing that to make a couple of points. So the graph of this function looks like this. Here, at x equals 0, the function is the smallest it ever gets. The value of f is 0 here, and every place else is greater than 0. We say that f attains a global minimum value. at x equals 0. Some people also say an absolute minimum value. I'll stick with global. Attains means there's actually an x-coordinate that makes f, or at which x takes on this minimum value. Over here, what happens when x is minus 1? Well, this isn't a global maximum value of f because f gets bigger over here, like the y-coordinate at points over here is bigger, or are bigger. But this is the biggest f gets anywhere near here. So for any x-coordinate near minus 1 and in the domain of f, this is the biggest the function ever gets because near here and in the domain we would just be looking at these points, and for those near x equals minus 1, this is the biggest y-coordinate on the graph. So we say that f attains a local, as opposed to global, a local maximum value at x equals minus 1. What about a global maximum value? Well, there is no global maximum value. As x gets bigger, bigger than 0, and as x gets bigger, f of x just gets arbitrarily big. We can make f of x as big as we want by picking x as big as we want. So f never attains a maximum value. There's no x-coordinate so that you can say, at that x-coordinate, f is the biggest it ever gets. There is no biggest it ever gets. It just keeps getting bigger and bigger. So for this function, this f does not attain a global maximum value. Functions don't have to attain global or local maxima or minima. Maxima and minima are the plural of maximum and minimum. We usually say maxima for maximum values and minima for minimum values. And the collective term for both maximum and minimum values is extreme values, or extrema. So f does not attain a global maximum in this example. There is an important theorem that tells you for some nice functions that they must attain extreme values, so global maxima and minima. It's not surprising that it's called the Extreme Value Theorem. And it says continuous functions on closed bounded intervals so that's just an interval of the form AB, including A and B, closed bounded intervals, attain global maximum and minimum values. That's the extreme value theorem. And in a way, you could say that the reason this function is allowed to not have a global maximum is because it fails the hypotheses of the extreme value theorem. Yes, this function is continuous, but its domain is the half-open interval from -1 to infinity. It's not bounded. It goes out infinitely far. It's not of the form a closed interval from A to B. So it's not, the extreme value theorem doesn't apply to it. Okay, so there is a relation between extreme values and derivatives, and that's the first, well, the next theorem that we want. The first answer to one of the questions that I ask about is the derivative working the way we want it to work? This is the kind of the answer to, you throw a ball up in the air, does the derivative have to be 0 when the ball reaches its maximum height? So theorem. If f is differentiable at x, and f attains a local extreme value, so either a local minimum value or a local maximum value. It doesn't have to be global, and f attains a local extreme value at x, then f prime of x has to be 0. I do want to sketch the proof of this for you, but let me give you an example other than a ball going up in the air, and make sure you know what it doesn't say before I sketch the proof of it. So let's go back to our function y equals x squared, but we're restricting x to being greater than or equal to -1. We saw that f has a global minimum where x is 0. This function is also differentiable at 0. It's x squared. We've already looked at its derivative. Its derivative is 2x. We've restricted the domain, and that causes a problem over here at -1, but it doesn't change the derivative at interior points of the domain, points other than the endpoint of this interval. So this function is differentiable, and the fact at x equals 0, and the fact that it attains a global minimum there, well, a global minimum is certainly a local minimum. If you're the smallest thing anywhere, you're the smallest thing near you. And so certainly f attains a local minimum at x equals 0, and it's differentiable there, so the derivative has to be 0 at x equals 0. So f prime at 0 has to be 0. Of course, we know that. The derivative of x squared is 2x. So yes, its derivative has to be 0 there. This theorem doesn't say anything about the value of the derivative of x squared at x equals -1. This function is technically not the same as y equals x squared. We've restricted the domain. This function with the restricted domain is not differentiable at -1, and that's important. The function is not differentiable at -1 because -1 doesn't have an open interval around it that's contained inside this domain. One of the criteria for the derivative to exist is first that for the derivative to exist at a point x has to be an interior point of the domain. It has to be a point so that an open interval around that point is contained inside the domain. That's not true at -1. This restricted function is not differentiable at -1. So this theorem doesn't say anything, well, I was about to say it doesn't say anything about what f prime of x has to be. Well, it says it doesn't exist. So, in fact, let me make a definition and rephrase this theorem. So, the definition, a point x in the domain of f is a critical point if and only if if and only if f is not differentiable at x, or f prime of x equals 0. So there are two things that can make a point in the domain of f. First, talk about something being a critical point of a function. It has to be a point in the domain. But then there are two ways it can be a critical point. Either the function is not differentiable at x, or the function has derivative 0. With that definition, what this theorem says is that if f attains a local extreme value, then either f is not differentiable, so it's a critical point, or if f is differentiable, then f prime would have to be 0, so it's a critical point. So with this definition, we can rephrase this theorem as if f attains a local extreme value, at x, then x is a critical point of x, of f, and x is a critical point. Of x. So phrased this way, the theorem does say something about this endpoint. This function does attain a local maximum when x is minus 1. And so this theorem says x has to be a critical point of x, yes, a critical point of f. The theorem says that x has to be a critical point of f. It's a critical point in the sense that the derivative, the f is not differentiable at x. So, okay, this theorem answers the question about throwing the ball up in the air, and does the derivative have to be 0 when the ball's at the top? Sometimes people read more into this theorem than it says. This theorem does not say. So, this is a warning. It is not true that every critical point is a point where f attains a local extreme value. So the converse of this theorem is not true. If f attains a local extreme value at a point x, then x is a critical point. It does not say if x is a critical point, then f attains a local extreme value. And perhaps the easiest example of this is y equals x cubed. The derivative of this, certainly once we have the power rule, this will be trivial, but the derivative of this function is differentiable everywhere, and its derivative is 3x squared. In particular, at 0, so I should draw this flatter, at 0, the derivative is 0. So y prime at 0 is 0. So x equals 0 is a critical point of this function, and yet the function does not attain a local maximum or minimum value at 0. For x slightly bigger than 0, you get bigger values. For x slightly less than 0, you get smaller values. So the function has neither a local maximum nor a local minimum at x equals 0. All right. Now I want to talk about the case of the car that averages 60 miles an hour. And did it ever have to go exactly 60 miles an hour? The theorem that's related to that is an extremely important theorem. It's called the mean value theorem. Typically, one proves Rolle's theorem, something called Rolle's theorem first, which is a special case. I'm going to state the mean value theorem for you and then kind of give you a rough sketch of Rolle's theorem and then just say something about how you get to the mean value theorem. So, the mean value theorem. Suppose that f is continuous on a closed interval from a to b and differentiable on the open interval from a to b. I am, of course, assuming a is less than b, but I'll write that explicitly. Suppose f is continuous on ab and the closed interval from a to b and differentiable on the open interval from a to b. Then there exists C in the open interval from a to b. So C is between a and b, not including a and b. Then there exists C in a, b such that what? Such that the instantaneous rate of change at C, instantaneous rate of change of f at C, so the derivative of f at C, is the average rate of change of f over the interval, on the interval from a to b. So that's f of b minus f of a over b minus a. This is the mean value theorem. It's extremely important. It follows quickly by doing a clever manipulation to the function and applying something called Rolle's theorem, which is a special case. So special case. This actually implies the general case very quickly. So let me mention the special case. This is called Rolle's theorem. And Rolle's theorem says exactly this, except suppose that f is continuous on AB, differentiable on AB, and assume f of a equals f of b. Then, so the conclusion of Rolle's theorem, so I should change this. This is now Rolle's theorem. Well, it should be this, but f of a equals f of b, so this is 0. So it's just this. There exists some c in ab such that f prime equals 0. It's actually easy to say why this is true given the stuff we already know. It's f of a, so here's a, here's b. F of a equals f of b. These are supposed to be at the same height. F of a equals f of b. And there should be a point between a and b where f prime of c is 0, so where the slope of the tangent line is 0. Why? Because f is continuous. It's a continuous function on the closed interval from a to b. So the function, by the extreme value theorem, f has to attain a global maximum and a global minimum between a and b. But f of a equals f of b, so either the global maximum doesn't occur at the endpoints, or the global minimum doesn't occur at the endpoints, because the global minimum can't be the global, well, actually that's not true. Suppose the global minimum were the same as the global maximum. Then the function is constant and you're finished. The If f were a constant function, its derivative is 0 everywhere, and you can pick any number between a and c, a and b. Assuming the global minimum and the global maximum that you get from the extreme value theorem are not the same, then one of them is not f of a, which is the same as f of b. So, in my picture, the global maximum would not be f of a, which is the same as f of b. The global minimum would be the global maximum. One of them must not be the same as f of a and f of b. But that means that the global maximum and the global minimum occurs at an interior point, somewhere between a and b. But we're assuming the function is differentiable there. And we just proved the theorem that if a function is differentiable, if the function is differentiable and it has a local extreme value, then at that point, the derivative has to be 0. And so you obtain Rolle's theorem. I just said that we proved that theorem. I kept talking about proving that theorem. And I never gave you the sketch of the proof that if a function is differentiable and it attains a local extreme value, then the derivative had to be 0. So now that I've just used that to give you Rolle's theorem, I should go back and give you a sketch of that proof. But let me finish messing with Rolle's theorem and the mean value theorem. That's Rolle's theorem, and then all you do to prove the mean value theorem from Rolle's theorem is come up with a new function g so that the conclusion of Rolle's theorem enables you to obtain the conclusion of the mean value theorem. We have a lot of other things to do in this section, including the proof that I omitted. So let me go back and do this proof and let you read about how you mess with the function that satisfies, or mess with the function f to make it satisfy Rolle's theorem, and then conclude the conclusion of the mean value theorem. So I want to go back and sketch the proof of if f is differentiable at x and f attains a local extreme value at x, then f prime of x must be 0. I'm going to pick whether I have a local maximum value or a local minimum value at x. The proof is the same either way, or essentially the same either way. So let me do, if f is differentiable at x and f attains a local maximum value at x. The proof for local minimum value, completely analogous. So what do you do? So a sketch of the proof for h close to 0. F of x plus h will have to be less than or equal to f of x. Why? Because we're assuming that x is a point where f attains a global maximum value, which means that for all other x values close to this specific one, that the value of f is less than or equal to this maximum one. So it means for h close to 0, x plus h would be close to x, that all the f values there are less than or equal to this maximum value. Great. Another way of saying that is that f of x plus h minus f of x is less than or equal to 0. Okay, so what do we do with that? Well, that should look like the numerator of the limit that we look at to define the derivative. And it is. And that is the key to the theorem. So consider the limit as h approaches 0 of f of x plus h minus f of x divided by h, which exists because it's f prime of x, and we're assuming that f was differentiable at x. This limit is the two-sided limit. When we talked about limits, we talked about the fact that the two-sided limit exists if and only if the two one-sided limits exist and are equal. So for this to exist, we have to have this limit from the left, so as h approaches 0 through negative h values, has to equal this limit from the right as h approaches 0 through positive h values. But what does this tell us? This f of x plus h minus f of x, this numerator is negative because f attains a local maximum value at x. The numerator is negative. As h approaches 0 from the left, the denominator, this is less than or equal to 0. It doesn't have to be negative, it could be 0. Numerator is less than or equal to 0. The denominator is less than 0, which means this quotient is greater than or equal to 0, and so the limit, which has to exist because the two-sided limit exists, that limit has to be greater than or equal to 0 because this quotient is always greater than or equal to 0. This limit, on the other hand, the numerator is negative, h is approaching 0 from the right through positive h values. That means that this quantity is always less than or equal to 0, and so this limit that has to exist is less than or equal to 0. So this number that's greater than or equal to 0 has to equal this number that's less than or equal to 0. There's only one way for that to happen. They both have to be 0, which means this is 0, which means f prime is 0. And that's how you prove that if f is differentiable at x and attains a local extreme value there, then the derivative is 0. All right. I'm sorry I forgot to do that when we were going over the proof, but yeah. And you use that in the proof of Rolle's theorem, and then you use Rolle's theorem to prove the mean value theorem. Maybe, I think we've got plenty of time. Let me go back and so we use that to prove Rolle's theorem. Suppose you've got this. Suppose now that we don't know that f of a equals f of b. We're in the general case of the mean value theorem. How do you manipulate the function f and produce something that you can use Rolle's theorem on to get the mean value theorem? And the answer is you define, we're going to define a g of x whose derivative we can calculate easily in terms of the derivative of f, and so that the conclusion of Rolle's theorem applied to g will tell us the conclusion of the mean value theorem applied to f. So you can think about it for a while. You consider, all right, consider this function, but then I still need to mess with this a little bit. But think about this. First of all, a and b are not equal. A is less than b. So this is just a constant. This is a constant times x minus a constant. We actually know how to differentiate that. So we've got this. When x is b, you get f of a minus, all right, when x is b here, you get b minus a times b minus a, those would cancel, or b minus a divided by b minus a, those would cancel. You get f of b minus f of a. So I am going to add to this We need an f of x in here somewhere. So I'm going to subtract f of x so that now when x is b, I get f of b minus f of a minus f of b, so I just get f of a, and I'm going to add f of a back. Try not to get lost. This is just a trick. So what's happening now? Why have I done that? It is, what's g of b? G of b is you get b minus a here, it wipes out that b minus a, you get f of b minus f of a, but then you subtract an f of b and you add an f of a. So g of b is 0. What's g of a? G of a is 0. Or I claim that it is. G of a, you plug in x is a, so you get 0 here, so this part becomes 0. And then you get f of a minus f of a. So g of a equals g of b equals 0. G is differentiable because f was differentiable, and all we've done is take constants times x and add or subtract constants. Here's a subtracted constant, there's added a constant. So f was continuous on the closed interval from a to b and differentiable on the open interval from a to b. G will satisfy the same thing. G of a equals g of b equals 0. So we're in the setting of Rolle's theorem to apply it to g. And the conclusion is, of Rolle's theorem, there exists C in the open interval from a to b such that g prime of c equals 0. But what's g prime of c? Well, we could do this. G prime of c is, this is just a constant times x minus a constant. Its derivative, we just get, if you multiply this times this is a constant times x minus a constant. The derivative is just the constant that's multiplied times the x. So we get f of b minus f of a over b minus a. And then you have the derivative of this. This is a constant. Its derivative is 0 minus the derivative of f at c. So minus f prime at c. Oh, but this was the conclusion we wanted. We get g prime of c is 0. So 0 equals f of b minus f of a divided by b minus a minus f prime of c. Put the f prime of c over here. That's the conclusion of the mean value theorem. Okay. Why do we care about the mean value theorem? For lots of reasons. It helps us prove lots of technical other things, but it also addresses that question of a car travels exactly 60 miles in exactly 1 hour. Shouldn't we be able to show that there's a time when the car went exactly 60 miles an hour? This is what the mean value theorem does for us. It tells us that, yes, look at the average value of a function over an interval. There is a point in time in that interval where the instantaneous rate of change equals the average rate of change. All right. We can use the mean value theorem to prove something that seems much more basic than the mean value theorem, namely that if the derivative of a function is 0, the function had to be constant. So, theorem. Suppose suppose the domain of f. So the places where f is defined. Suppose the domain of f is an open interval. I, and f prime of x equals 0 for all x in I. Then f is constant on I, i.e. there exists a number, a constant. How do you prove this? It's easy for us now that we have the mean value theorem. So suppose we've got a function defined on an open interval, and the derivative of the function is 0 everywhere. So, proof, use the mean value theorem, which I'll abbreviate, MVT, mean value theorem. Right? So, what's the same as saying that the function is constant? It's the same as saying all the f values are the same at all the points in the interval. Proof, use the MVT. Suppose A and B are points in the interval, and I'll let A be the smaller one. So I can, if B were the bigger one, I'd change its name and call it A. I'd switch the name. Suppose A and B are points in I and A is less than B. Then, well, now we could apply the mean value theorem to this function f and on the closed interval from A to B, because f is differentiable, because its derivative 0, f is differentiable, so it's continuous. Then apply the MVT, the mean value theorem, to f on the closed interval from A to B. F is continuous on this interval, it's differentiable on the open interval. The conclusion of the mean value theorem, apply the mean value theorem to conclude there exists C. In AB such that f prime of C equals f of B minus f of A over B minus A. Yeah, but C is in between A and B, and I is an interval, so C is also in the interval. And f prime of C then has to be 0, because we're assuming that the derivative is always 0. So we get that this is 0, but that means f of B equals f of A. So in other words, we've shown that no matter what two x values you take in the domain of f, no matter what two x values you take in I, the function has the same value everywhere. Yeah, so the function's constant. So you probably would have assumed that even had we not proved it. I mean, we proved that the derivative of a constant is 0, and it's just so intuitively obvious that if the rate of change of a function is 0, it should be constant, that you probably would have assumed this without proof. But there's the proof. Kind of a corollary of it that is easy but important. Corollary: if f prime equals g prime, so two functions have the same derivative at all points in an open interval, then f and g differ by a constant. That is, f equals g plus c for some constant c. So maybe I'll write it as f of x equals g of x plus c for all call the open interval I for all x and I. So by this I mean there exists this one constant c that works for all the x's and i's. So f and g differ by a constant. How do you prove that? Well, you just look at f minus g and its derivative. Then since f prime equals g prime, the derivative of f minus g is 0. And then by the other theorem we proved, if its derivative is 0 on an open interval, then it equals a constant. Then you put the g on the other side. Why is this so important? Well, consider the following problem. Find all f of x, so all functions f from r to r that are differentiable. So the domain of f is r. The codomain is r too, but really it's the domain that we care about so much. The domain of f is r. Find all such that df dx, so the derivative of f with respect to x is x squared. What this theorem, this corollary tells us is that if we could find one function whose derivative is x squared, then every other function f whose derivative is x squared differs from that one by a constant. So if we could find a function whose derivative is x squared, every other function whose derivative is x squared is that one we find plus some constant. Well, how do we find a function whose derivative is x squared? Well, we kind of just know, in a sense, or we will know. Actually, I wrote this earlier. Assuming that we know that the derivative of x cubed is 3x squared, we have this. If we divide both sides by 3, we have this. Now, the derivative of a constant times something, you can pull the constant out. Well, we can do that in reverse and put the constant inside. So the derivative of 1/3 x cubed is x squared. So here's something whose derivative is x squared, and that means every other thing whose derivative is x squared looks like this one plus a constant. So what are all the functions whose derivative is x squared? The answer is that all of them would look like f of x is 1/3 x cubed plus some constant. And you can't, every function that satisfies this looks like this, and everything that looks like this has derivative x squared. You can't determine what this constant is without some more data, like possibly being told that if you were told the value of f when x is something, like if you were told the value of f when x is 1, for instance, if you know, if f of 1 equals 7, if you were told this ahead of time, and df dx equals x squared, then you can solve for c. Then you would get, 7 equals f of 1, but that's 1/3 plus c, and then you solve for c. C is 7 minus 1/3, so 21/3 minus 1/3, 20/3, and you could find exactly what f was. All right, the last topic in this section that I want to talk about is increasing and decreasing functions. There's a lot of terminology that comes in here, and again we will apply the mean value theorem to reach our conclusions. So we'll go back to our old friend y equals x squared, but without chopping off the domain this time. So here's the graph of y equals x squared. Over here, when x is less than 0, the function roughly goes from the upper left to the lower right. That means that as the x-coordinates are increasing, the y-coordinate is decreasing. Over here, as the x-coordinates increase, the y-coordinates increase. So the graph roughly goes from the lower left to the upper right. We call this kind of thing increasing. And this decreasing. So let me, I'll write this, and there's some qualifying terms that we've put on it, but this is the big deal. It's whether as x gets bigger, does f of x get bigger or does it get smaller? Or it could stay the same, which is part of the reason you have all these technical definitions. So suppose you've got some function f. So suppose f is defined on an interval I. Then f is, we say, monotonically increasing on I. It's a cool word, monotonically. Monotonically increasing on I, if and only if and only if what? If and only if for all A and B in I such that A is less than or equal to B, f of A is less than or equal to f of B. This is monotonically increasing. What does it say? It says if you take an x-coordinate that's greater than or a bigger x-coordinate, or possibly the same, then you get a bigger f value, or possibly the same. This allows for the possibility that A could be less than B, strictly less than B, not equal to, but that A could be less than B, and still f of A could equal f of B. So this allows for, yes, it's not necessarily true that as the x-coordinate's getting bigger, f is getting bigger. It's as the x-coordinate gets bigger, f is either staying the same or getting bigger. So some books refer to this as non-decreasing. There's a lot of terminology that's slightly different from book to book here, and you need to be careful. We're going to use monotonically increasing to mean this. Some books would say non-decreasing, some would just say increasing, some would say weakly increasing. There's a whole bunch of different terminology out there. I'm going to call this monotonically increasing. If I want the stronger condition that bigger x values imply bigger f values, then I'll call that strictly increasing. So f is strictly increasing. Oh, strictly increasing. And that means if A is less than B, f of A is less than f of B. So that bigger x values definitely give you bigger f values. That's strictly increasing. Strictly decreasing, you have the analogous thing, but it means if A is less than B, then as your x-coordinate goes up, the value of your function goes down. So the bigger x value gets you the smaller f value. And then, of course, there's monotonically decreasing, which some books would call non-increasing. So it allows for the possibility that a bigger x value gives you the same f value. So there's monotonically decreasing. And that is A is less than or equal to B implies f of B is less than or equal to f of A. Anyway, don't get too caught up in monotonically increasing and decreasing versus strictly increasing and decreasing. Yes, strictly is what we expect most of the time, that a bigger x value produces a bigger f value, or a smaller x value, or a bigger x value produces a smaller f of x value, depending on whether you're strictly increasing or strictly decreasing. What does this have to do with derivatives? Well, as we've kind of talked about intuitively, you can see it in the graph where a function is decreasing, so where it's headed from the upper left to the lower right, the slopes of the tangent lines are negative. Well, that makes perfect sense. If the rate of change of something is negative, you should mean it's decreasing. And over here, where the function is increasing, the rate of change, the slope of the tangent line, should be positive. Great. What's the theorem that tells us this? And again, you get this from the mean value theorem. Theorem is, suppose f is differentiable. I could state this with weaker hypotheses, but let's just do this kind of easiest phrasing, the one that comes up the most often. Suppose f is differentiable on the open interval I. Then if f prime of x is greater than 0 for all x in I, then f is strictly increasing on I. If f prime is greater than or equal to 0, then f is monotonically increasing. This shouldn't be surprising. I'm now saying, oh, I'm allowing for the possibility that the derivative of f is 0, but you should think, oh, the derivative of f is 0. It's not changing, so maybe as the x value gets bigger, the function stays the same, which is what monotonically increasing allows for. So if, for all x in I, then f is monotonically increasing on I. And 3 and 4 are the analogous things. Let me just alter these. 3 would be if this is negative for all x in I, then f is strictly decreasing on I. And 4, if f prime of x is less than or equal to 0 for all x in I, then f is monotonically decreasing on I. So these things that you expect to be true are true. How do you prove these? Well, they follow from the mean value theorem. Again, let me just do one of them, actually. You kind of do all of them at once. So suppose A and B are in I. And again, I'll assume that A is the smaller of the two. So they're different, and A is the smaller one. Then, since f is differentiable on the interval, it's definitely continuous on the closed interval from A to B, and it's differentiable on the open interval from A to B, so by the mean value theorem. So by the MVT, there exists C in AB such that f prime of C equals f of B minus f of A over B minus A. But now this handles every case. I is an interval. So if A and B are in I, everything in between A and B is in I. So C being between A and B, C is back in I. F is differentiable there. And its derivative equals f of b minus f of a over b minus a. But a is less than b. So this denominator is positive. So the sign of this, whether it's positive, negative, or 0, is just dependent on the numerator. This is positive, negative, or 0 if and only if the numerator is. But this is positive, negative, or 0 depending on which case we're in. So for instance, in 3, suppose f prime of x is less than 0 for all x and I. Then this is less than 0, which means this numerator is less than 0, which means f of b is strictly less than f of a. So that means a less than b implies f of b is less than f of a. That is what strictly decreasing is. Or if you're in the monotonically decreasing case, that would be where this is less than or equal to 0. So if that's less than or equal to 0, this numerator is less than or equal to 0. So you conclude if a is less than b, f of b is less than or equal to f of a. So f is monotonically decreasing. Right? So you use the mean value theorem to conclude these things. All right. This is an interesting word, monotically. This is monotonically. All right. I know this section is fairly technical. It's not like there are a lot of nice physical examples, except what you're supposed to get out of this section is that the derivative is defined and has the properties we need it to have for all these things that seem intuitively true to be true. That the rate of change being positive means a function's increasing. That the derivative, the rate of change of a function being 0 means the function is constant. You know, those things, if they weren't true, there's something wrong with the definition of the derivative. But what we know after this section is that they are true. There's nothing wrong with the definition of the derivative. And next time we'll do more down-to-earth physical examples and not so many proofs and ideas of proofs.